For decades, astronomers believed the early universe followed a relatively predictable timeline. After the Big Bang, the cosmos cooled, the first stars ignited, galaxies slowly assembled, and black holes gradually grew over hundreds of millions of years. It was a neat story, supported by decades of observations and computer simulations. Then the James Webb Space Telescope arrived, and almost immediately, it began rewriting the script. Within months of beginning scientific operations, Webb started sending back images of galaxies that simply shouldn't have existed so early in cosmic history. Massive, bright, and surprisingly mature, these ancient galaxies appeared just a few 100 million years after the Big Bang. Some contained enormous amounts of stars. Others appeared to host supermassive black holes already weighing millions, or even billions, of times the mass of our Sun. To astronomers, this wasn't just surprising. It was deeply unsettling, because if these observations are confirmed, they suggest that some of our best theories about how the universe evolved may be incomplete. And while no one is claiming physics is broken, there's growing evidence that something important is missing from the picture. This is what James Webb detected that no one expected to see. The James Webb Space Telescope wasn't designed merely to take prettier pictures than Hubble. Its true mission was far more ambitious. Webb was built to look farther back in time than any telescope before it. Since light takes time to travel, observing distant galaxies means seeing them as they existed billions of years ago. Looking far enough away allows astronomers to witness the universe during its infancy. Webb's enormous gold-coated mirror, spanning 6.5 meters, collects infrared light that Hubble simply couldn't detect with the same sensitivity. This makes it possible to peer through clouds of dust and observe objects whose light has been stretched into infrared wavelengths by the expansion of the universe. Scientists expected Webb to discover the earliest galaxies. What they didn't expect was how developed those galaxies would already be. According to the standard cosmological model, galaxies begin as small clumps of gas and dark matter. Gravity slowly pulls more material together, stars begin forming, and over hundreds of millions, or even billions, of years, these structures merge into larger galaxies like the Milky Way. This gradual process has been the backbone of modern cosmology. But Webb started finding galaxies only 300 to 500 million years after the Big Bang that appeared remarkably massive. Some contained hundreds of billions of stars, or at least enough light to suggest astonishing stellar masses. Astronomers jokingly called them universe breakers, not because they literally violate physics, but because they seemed impossible under existing models. If these galaxies really formed so quickly, then either galaxies can grow far faster than scientists believed, or our understanding of the early universe is missing something fundamental. Initially, many researchers suspected measurement errors. Perhaps these galaxies weren't actually as distant as they appeared. Maybe dust was making them look brighter than they really were. Or perhaps their masses had been overestimated. After all, extraordinary claims require extraordinary evidence. So astronomers began conducting follow-up observations using Webb spectrographs. Some early candidates indeed turned out to be closer than first estimated, but many didn't. Instead, the follow-up studies confirmed that several surprisingly massive galaxies genuinely existed astonishingly early in cosmic history. This shifted the debate. The question was no longer whether these galaxies existed. It became how they formed so quickly. One possibility is that stars formed much more efficiently in the early universe than today's models assume. Perhaps enormous clouds of hydrogen collapsed rapidly into stars without many of the processes that slow star formation today. Another possibility involves dark matter. Dark matter makes up roughly 85% of all matter in the universe, yet nobody knows exactly what it is. It provides the gravitational scaffolding that allows galaxies to form. If dark matter behaves differently than current theories predict, galaxy formation timelines could change dramatically. Some researchers have even proposed modifications to dark matter itself, suggesting new particle properties that could accelerate the birth of galaxies. Others believe the answer lies in improving computer simulations. The universe is incredibly complex. Simulations cannot include every physical process in perfect detail. Better models incorporating stronger gas inflows, faster cooling, or more intense bursts of star formation might naturally produce Webb's observations without overturning cosmology. But galaxies weren't the only surprise. Webb also detected evidence suggesting enormous black holes existed astonishingly early. This may be an even bigger mystery. Black holes form when massive stars collapse. Those stellar black holes then slowly grow by consuming gas or merging with other black holes. At least, that's the traditional picture. The problem is speed. Imagine starting with a black hole around 100 times the sun's mass. Even if it continuously consumed surrounding matter at the maximum theoretically stable rate, growing into a billion solar mass monster should take much longer than the universe had existed when Webb observed some of these objects. Yet several distant galaxies appear to host gigantic black holes less than a billion years after the Big Bang. Some may have reached enormous masses in only a few 100 million years. It's like finding a fully grown skyscraper in a town that was supposedly founded last week. Something doesn't add up. One explanation suggests these black holes didn't begin as ordinary stellar remnants. Instead, they may have formed through what's known as direct collapse. Rather than a star exploding first, immense clouds of primordial gas could have collapsed directly into black holes, tens of thousands, or even hundreds of thousands, of solar masses. Starting larger dramatically reduces the time needed to reach supermassive sizes. Another possibility is that early black holes consumed matter at rates exceeding what scientists previously considered sustainable. Under special conditions, black holes may briefly grow faster than conventional models allow. Neither explanation has been proven, but both are now receiving far more attention because of Webb's discoveries. Then came another unexpected observation: chemical complexity. The early universe should have consisted almost entirely of hydrogen and helium. Heavier elements such as oxygen, carbon, silicon, and iron are forged inside stars and distributed into space when those stars die. Finding chemically enriched galaxies means multiple generations of stars had already lived and died. Webb has identified galaxies surprisingly rich in heavier elements at extremely early times. This suggests stars may have formed, evolved, exploded, and recycled material much faster than expected. Again, not impossible, just surprisingly fast. Each discovery alone might be explained individually. Together, however, they paint an increasingly intriguing picture of an early universe that evolved with astonishing speed. Naturally, headlines began claiming Webb had disproved the Big Bang. That's not what happened. The Big Bang remains overwhelmingly supported by multiple independent lines of evidence, including the cosmic microwave background, the expansion of the universe, and the abundance of light elements. Webb hasn't invalidated these observations. Instead, it has challenged specific details about what happened after the Big Bang. Think of it like discovering that human civilization advanced much faster than historians thought. You wouldn't conclude humans never existed. You would revise the timeline explaining how civilizations developed. That's precisely what astronomers are doing today. Some researchers are exploring entirely new ideas. Could unknown forms of dark matter have accelerated structure formation? Did exotic conditions in the infant universe trigger unusually rapid galaxy growth? Could the first generation of stars have been vastly larger than today's stars, producing heavier elements and massive black holes far earlier? These possibilities remain speculative. Science hasn't reached a consensus. And that's exactly why Webb's discoveries are so exciting. Great scientific breakthroughs often begin with observations that don't fit expectations. When Uranus deviated from its predicted orbit, astronomers didn't immediately abandon gravity. Instead, they searched for another planet. That search led to Neptune. When Mercury's orbit refused to match Newton's laws, scientists eventually developed Einstein's theory of general relativity. Unexpected observations don't necessarily destroy old theories. They reveal where our understanding can improve. James Webb may be doing exactly that. Its discoveries are forcing astronomers to ask better questions, refine their models, and test new ideas about the universe's earliest moments. What's remarkable is that Webb has only begun its mission. The telescope is expected to operate for many years, continually collecting deeper observations of the ancient cosmos. Every new observing cycle provides astronomers with additional opportunities to verify earlier discoveries, identify new anomalies, and distinguish genuine surprises from observational bias. Future telescopes, including the Nancy Grace Roman Space Telescope and next-generation ground observatories, will work alongside Webb to build an even clearer picture of cosmic history. Some mysteries may disappear as more data arrives. Others may become even more puzzling. That's the nature of scientific discovery. The biggest revolutions rarely happen because scientists set out to overturn established ideas. They happen because nature refuses to behave exactly as expected. James Webb hasn't shown us that everything we know is wrong. Instead, it has revealed that the universe is more complicated, more dynamic, and perhaps far more efficient at building galaxies, stars, and black holes than anyone imagined. And perhaps that's the most astonishing discovery of all. Not that the universe broke our theories, but that, after centuries of studying the cosmos, it still has the power to surprise us,